All right, welcome back to another calculus lecture video. In today's lecture, what I want to talk about is another strategy for differentiating certain functions known as logarithmic differentiation. And to motivate this, maybe let's just do a quick example. So, example. Suppose that we want to compute the derivative of x squared e to the x cosine of x divided by, I don't know, x plus 3 squared times, I don't know, tangent inverse of x. We'll get spicy. Okay, so if you want to compute this, so we'd probably need to use the quotient rule. So we probably need the quotient rule. And we probably also need the product rule, because we have a quotient of things, and in each one of those things that we're dividing, we have a product of things, and in one of those, we actually have a composition. So product rule a few times, because we're going to have to differentiate this product, and then the more general thing of this thing times cosine of x, so we're going to have to apply the product rule like twice. Product rule a few times. And we probably need the chain rule to compute this derivative down here. Please no. Please let's not do this. No. Please, no. Let's not just start computing this derivative, because this would just be very, very hell to compute, really. So we're not going to do that. Well, we will compute this derivative, but we're not going to do it in the very long and complicated way of using all of these different rules to compute this derivative. So I've hinted at the fact that we don't want to use those rules, so how do we do this? Well, let's make an observation here. So observation. So the observation is this: if I want to compute the derivative of a product, f of x, g of x, well, this gives me some sort of complicated, well, not really complicated, but it's not super friendly. It splits up into a pair of terms. So if I want to compute a product, then I have to use the product rule. But if I want to compute a sum, notice what happens. Well, to compute the derivative of a sum, the derivative is linear. So I just compute each of the individual derivatives and add them together. Oh. Meh. There we go. F of x plus g of x. Well, prime. Well, that's a little bit easier than doing the product rule. It's at least fewer steps. Well, what happens if I have three functions and I want to compute the derivative of that? So d dx of f of x, g of x, h of x. And I haven't shown this before, but you could go through and work this out. The derivative of a triple product is similar to this, except that you have three terms and you just do one derivative per term. So this is going to be f prime of x, g of x, h of x, plus f of x, g prime of x, h of x, plus f of x, g of x, h prime of x. Okay, well, this is getting complicated very quickly. This is just a big expression that I really don't want to have to deal with. Well, notice what happens if I have just the derivative of a sum of three functions. Well, it's the same thing as before. The derivative is linear. So this is just going to be f prime of x plus g prime of x plus h prime of x. So taking the derivative of a sum is a whole lot easier than taking the derivative of a product. So let's write that down. Sums are much easier to differentiate than products are. And so, if at all possible, we'd prefer to compute the derivative of a sum rather than the derivative of a product or a quotient. Really, you can think of a quotient as just the product of a function and the reciprocal of another function. Okay? So, that begs the question, color black, sure, question, is there a way to turn products into sums? That is, can I just alter my perspective a little bit when computing these derivatives and instead compute the derivative of a certain sum where that sum, in a way, corresponds to the product of the things I was interested in? The answer is yes. Thankfully. If the answer was no, then this would be a very stupid lecture. But the answer to this question is yes, we can turn products into sums, and the way that we do that is through logarithms. So, recall that if I take the logarithm of a product, so the natural log of, and we'll just do f of x times g of x, well, what is one of the properties of logarithms? Logarithms will split a product into a sum. So this will be the natural log of f of x plus the natural log of g of x. And now if I want to compute this thing, well, I can compute just the left-hand side using the chain rule and what I know about the derivative of the natural logarithm. And on the right, I can do the same thing, but I can compute the derivative using each of the individual terms. And so that will be much easier in the long run. So let's maybe state this identity. And also, let's just recall what the derivative of the natural log function is. Dx of natural log of x, this is equal to just 1 divided by x. Okay, so all that happens is you take what's inside the natural logarithm function and you put it in the denominator of a 1 over that thing. Okay, so let's put all of this together. And maybe we'll switch to blue. So this leads us to logarithmic differentiation, and it's really just a fancy way of saying that we're going to take a derivative of a logarithm and use the chain rule. So logarithmic differentiation says that the derivative of the natural log of a function, so what I'm going to do, instead of computing the derivative of the function itself, I'm going to compute the derivative of the natural log of that function. Well, this is equal to, what do? I divide by 1 divided by whatever is in here, so I get 1 over f of x. And then what does the chain rule tell me I have to do? The chain rule tells me I have to multiply by the derivative of what's inside. So this is going to be times f prime of x. Anyways, you can see the little multiplication dot there. Okay, so, well, notice what's happened here. The thing I'm interested in, the derivative of f, has actually popped out of this derivative right here, of the derivative of the natural log. And so, f prime of x is equal to, well, let's just isolate f prime of x on the right-hand side by multiplying the f of x over. So this is equal to f of x times the derivative of the natural log of f of x. And this is really the main identity. I should have centered it in the page to really emphasize it, but alas. Okay, so, and notice we've used no facts about f of x. This works for any function that is differentiable. And so if I want to compute the derivative of f of x, it suffices to actually compute its logarithmic derivative. And as we've seen, that is potentially much easier to do than the derivative of f of x itself. So let's return to our example. Revisited. Okay, I'll cut the video there just so you don't have to watch me flipping back and forth to copy this big thing. So I'm interested in computing this, so let's let this whole thing be our f of x function. And let's compute the natural logarithm of it. So let f of x be that function. Then what happens when I compute the natural logarithm of this? So the natural log of f of x is equal to, well, I can sort of do this in a few different steps, but maybe I have a quotient. So remember, logarithms take products to sums and they turn quotients into differences, just because a quotient is just sort of the inverse of multiplication, so that's why that's happening. So the natural logarithm, when I take this, I'm going to have the logarithm of the top minus the logarithm of the bottom. So this is going to be the natural log of x squared e to the x cosine of x minus the natural log of x plus 3 squared times tangent inverse of x. Okay, well, now I have products in each of my natural logarithms, so let's go ahead and split those up using the properties of logarithms. So this is going to be the natural log of x squared plus the natural log of e to the x plus the natural log of cosine of x minus the natural log of x plus 3 squared. And then the minus sign distributes to each of the two things in the product, so this is going to be minus the natural log of tangent inverse of x. And now what we can do is to make our life even easier, we can simplify these expressions using the properties of logarithms as they pertain to exponents. So, and I'm going to move the equality over here just so I have more room. So the 2 here, remember the natural log of something to a power, it pulls the power down in front as a scalar. So this is 2 times the natural log of x. Natural log of e to the x, these are inverse functions, so this is just going to be plus x. Natural log of cosine of x, well, that doesn't really simplify any, so we'll just keep that as it is. Minus, there's a 2 right here, so that'll come down in front. 2 times the natural log of x plus 3. And then this negative 1 is not an exponent, it's just sort of notation that's used to indicate the inverse function. A little bit unfortunate, and perhaps we should use the arctangent notation, but that also, like the other trig function, does not change. Okay. So I've computed the natural log of f of x and simplified it. The simplification step is really important because it simplifies our life a whole lot. So now, well, if I want to compute the derivative of this thing, then it suffices to compute the derivative of the natural log. So let's do that. So we have d dx of the natural log of f of x Well, let's just go through and differentiate each of these things term by term. 2 times the natural log of x. This is going to give me 2 divided by x, so 2 times 1 over x is the same thing as just 2 over x. Derivative of x, well, that's just 1. That's nice and easy. The derivative of natural log of cosine of x, I'm going to get cosine of x in the denominator, and then its derivative up in the numerator, which is negative sine of x, minus, and again I have 2 times 1 over x plus 3. I should multiply by the derivative of x plus 3 from the chain rule, but the derivative of x plus 3 is just 1 because, well, you can compute that yourself. And then minus the natural log, the derivative of the natural log of tangent inverse of x. Well, we know that that's going to be 1 divided by tangent inverse of x, and then what did we say the derivative of tangent of inverse of x was last lecture? That is 1, so times 1 over 1 plus x squared. And maybe we'll just put this in parentheses to indicate that it is indeed multiplication. And now we can simplify things a little bit. This is going to be 2 over x plus 1. This is minus tangent of x, so minus tangent of x, minus 2 over x plus 3, minus 1 over 1 plus x squared, times tangent inverse of x. And my writing here is a little bit small. I apologize for that. But there we go. We've computed the derivative of the natural log of x. And we had to apply the chain rule a few times, but that pales in comparison to having to do the quotient rule followed by the product rule 4 times and then the chain rule a couple of times. This is worlds easier than that. And if you don't believe me, then go and try and compute this using the product and quotient rules. Have fun doing that. You won't, by the way. So we've got our derivative of our natural log. Let's go ahead and just write down what the derivative is. So f prime of x is equal to f of x times the derivative of the natural log of f of x and this is going to equal, well, we can write down what f of x is. It's this big thing. It's x squared e to the x cosine of x divided by x plus 3 quantity squared times tangent inverse of x. And then we multiply this by everything that's up here. So actually, we'll just make this parentheses bigger. So we have 2 over x plus 1 minus tangent of x minus 2 over x plus 3 minus 1 over 1 plus x squared times tangent inverse of x. And we're done. We're not going to simplify this anymore. I think this pen is now also running out of ink. How sad. No more simplification. Because I don't want to. And notice if you were to actually sort of take this and distribute this function term by term, what you would actually end up with is the derivative of this thing after you simplified it a little bit using the product and quotient rule. Of course, you're going to get the derivative either way. That's what this says up here. But if you were to apply the product and quotient rule several times to this thing and then simplify it, you would end up with, and you could factor out that original function and then write your final answer in this form. Logarithmic differentiation gives you a way to see that much more quickly. Okay, so this is the really nice technique for differentiating products and quotients. Again, the key idea is that logarithms take products and quotients and they convert them to sums and differences, which, morally speaking, are much easier to differentiate than products and quotients. Okay, so that's everything for this video. You'll have a few questions in your homework about computing derivatives like this, but we won't do too much more with logarithmic differentiation. I just wanted to make sure I showed this to you, and so that you know that it is a technique that you can use for computing derivatives. Okay? So, see you all in the next video.